In this lesson, we're going to look at Z-scores. The standard normal distribution is a normal distribution with mean mu of 0 and a standard deviation sigma of 1. The area under the curve of a normal distribution is 1. So if you remember in the last lesson, we were looking at if our data would fit a normal distribution. We looked at our histogram and we looked at our frequency polygon, and we could see that our curve fit that normal distribution curve. We were dealing with actual data. Now what we're going to be doing in today's lesson is we're going to fit the normal curve to the Z-scores. So instead of us talking about what the mean is, like we did in previous lessons, we didn't have 0 sitting there. It was the mean, or the average of all of our data. We're going to call that 0. And instead of adding a standard deviation to it, we're just going to call the standard deviation 1. So 0 plus 1, 0 plus 2, 0 plus 3. So every time we're dealing with data, we're always going to be looking at these numbers at the bottom, even though we're dealing with different situations. So for example, if I go back here to, let's see, this lesson, this example here, our mean was 23, and then our standard deviation was 1.5. So we added 1.5 every time we went up another interval, and we subtracted 1.5 every time we went down. Instead, what we're doing is we're superimposing the Z-scores. So we would call this 0, we would call this 1, 2, and 3, minus 1, minus 2, and minus 3. The data is still there, the mean is still there, but these are what we're calling this. The percentages are still there as well. But we're relabeling those values, knowing that a Z-score of 0 means 23, a Z-score of 2 means 26, a Z-score of negative 3 means 18.5. Alright, let's get back to this page here. So it says Z-scores can be used to compare data from different normally distributed sets by converting their distributions to standard normal distribution. So that's what I was talking. So now we're calling these new names. 0, 1, 2, 3, 0, negative 1, negative 2, negative 3. And again, what's missing in our diagram here is the 0.15%. Alright. So a Z-score indicates the number of standard deviations the data value lies from the mean. It is calculated using this formula. So this is an important formula that you're going to want to make note of and come back to. A positive Z-score indicates that the data values lie above the mean. So these are our positive Z-scores. Whereas a negative Z-score means that the data lies below the mean. The area under the standard normal curve to the left of a particular Z-score can be found in a Z-score table or determined using a graphing calculator. I'm going to show you how to do that. Okay? So when we're looking at this, when we talk about X, that refers to the actual score. When we have mu, the symbol mu, that refers to the population or sample mean. And when we talk about sigma, and sometimes a little s there, that refers to the population standard deviation. Alright, let's take a look at example 1 and how to use this formula. In example 1, they say there's person 1 has a score of 206, a mean of 190, and a standard deviation of 8. Person 2 has a score of 91, a mean of 81, and a standard deviation of 4. We don't really know what they're measuring here, but whatever they're measuring, we want to figure out what is the Z-score that is associated with this. So if we use our formula says that Z is equal to X minus mu over sigma. So in this case, Z is equal to X, which is our score, 206, minus the mean, which is 190, divided by the standard deviation. And when you do that, oops, the standard deviation is 8. Make sure you're using brackets in your calculator, or the calculator isn't going to use order of operations. And you should get a Z-score of 2. Okay. Now for this other one, say math, we'd have 91 minus 81 divided by 4, and we get a Z-score of 2.5. So what does that mean? Okay, well, person 1 has a better score than person 2, but if we were to draw this, right, the normal distribution for person 1, well, this means we've got a Z-score of 0, 1, 2. And if we go backwards, -1, -2, -3. And in terms of our shading, what we can see here, because if we look back to this page, it says that this indicates the number of standard deviations that the data lies from the mean, right? A positive Z-score indicates that the data value lies above the mean, and a negative Z-score is below. And it says the area under the standard normal curve is to the left of a particular Z-score, and that can be found in this table. So when I'm drawing my picture, all of those things are true, right? Positive Z-score is on the right, okay? But the area is everything to the left of that. So if I were to shade my area, and I'm just going to use a highlighter here so that you can still see what's going on, that would be everything in this region, right? That would be the total area up to and including 2. Now, if we were to draw that for this other person, it would look very similar, except we're not going all the way to 3, because this person only has a Z-score of 2.5, so that would be in between. So that would be up to, up to and including 2.5. So you are required to shade the area that is under the curve of a given Z-score, and that's the expectation when you're showing your work, is to draw the picture and shade it. If you want to shade with a highlighter, you could do that. If you want to just shade with your pencil, then you can do that, whatever works for you. But I'm going to look for these diagrams with the shaded region. Okay? So if we look at this, we can see that for the first person, there's two standard deviations above the mean. The other person's 2.5 standard deviations above the mean, and person 2 has a better score. Alright, let's take a look at another example. Example 2 says a certain brand of flashlight battery has a mean life of 40 hours. I like this example because we've got some context. In the first example, we didn't really know what those numbers meant. Now, 40 hours for the mean life and the standard deviation of 5 hours. Find the Z-scores of batteries that last 50 hours, 35 hours, and 40 hours. So, if I just draw this, you don't have to draw this. I'm going to erase it in a minute. But if we have this normal distribution, that means that on average, right, mean would be 40 hours. Now these other batteries will lie above and below the mean. Well, 40 hours, you would think that would be right at the mean. We would anticipate that that's going to give us a Z-score of 0. So this one's going to be a Z-score lower than 0, where 50 hours should be a score that's higher than 0. Now where that exactly is, well, 5 is our standard deviation. So 1 standard deviation above the mean would be 45. 2 standard deviations above the mean would be 50. So you can see, so that would be at 2. You can see where that would be, and 1 standard deviation below the mean would give us 35 because you're subtracting 5. When we use our formula, we should find that this is a Z-score of 0, this is a Z-score of 2, and this is a Z-score of 1. Okay, I'm going to erase all this, and let's see if that actually holds true. Now these are nice small numbers, easy to figure that out, but that's not always going to be the case. So it's really nice, even for ones that we know the answers to, let's make sure we understand how to use the formula. So our Z-score here our formula is x minus mu over sigma. So for this first one, our z-score would be 50 minus 40 over 5. Well, 50 minus 40 is 10. 10 divided by 5. Well, that gives us a z-score of 2, like we anticipated. For the next one, it would be 35 minus 40 divided by 5. So 35 minus 40, that gives us a negative 5 divided by 5, and that gives us a negative 1. So you can see, in order to get a negative z-score, your score must be lower than the mean. And for the last one, we've got 40 minus 40. Well, when your score is the same as your mean, you end up with a 0. So 0 divided by 5, that gives us a z-score of 0. Alright, example 3 is a little different. Find the actual score given the z-score, the mean, and the standard deviation. So we're solving for x in this situation. So if I remember the formula, x minus mu over sigma, the mean is 100. I don't know x. I know that my standard deviation is 12, and in this situation the score is 1.5. So solve for x. How do I do that? Well, first get rid of the 12 by multiplying 12 by both sides. Well, that gives me 12 times 1.5, which is 18. And then that's x minus 100. Then I want to get rid of the 100, so add 100 to both sides. That creates a 0 pair, and I'm left with 118 is equal to x. So the actual score that you're looking at is 118. So if you see a z-score of 1.5 for this situation, that's associated with a value of 118. Go ahead and try the other two. So z-score 2 is 0, z-score 3 is negative 2.25. I'll give you a moment to do that, and you can come back and check with my answer. Alright, so you should have got a z-score of 0 was a 100, which makes sense because that's our mean, and a z-score of negative 2.25 is 73, which makes sense because it's below the mean. Alright, let's take a look at another example. Example 4 says, a skill test was given to 100 secretaries. The mean score was 35, and the standard deviation was 2.6. If Steve has a z-score of 1.56, what is his actual score? Alright, so using our formula again, we know that there was 100 secretaries, the mean score was 35, that's important. Standard deviation was 2.6, and his actual score, his z-score is 1.56. We want to know his actual score, so we're solving for x. So z is 1.56, x we don't know, the mean score was 35, and the standard deviation is 2.6. So let's go and solve for x. So multiply both sides by 2.6. And we get that these cancel out. 2.6 times 1.56 is 4.056. So add 35 to both sides, and you end up with an actual score of 39.056. Now you can see that as these numbers change on this side here, you're going to have numbers in your calculator. So if you can hold those in your calculator, when you add the 35, you're going to have a more accurate result in the end than if you were to have rounded that. And sometimes you only have 3 decimal places, but sometimes you have a whole trail of decimal places. Try to keep those all in your calculator and then round at the very end. Alright, go ahead and try B on your own, and then you can see who had a better actual score. If Alice has a z-score of 2.48, what was her actual score? Well, a z-score of 2. Oops, that's not a highlighter. If you have a z-score of 2.48 and a z-score of 1.56, who should have the higher score? Right? You would think 2.48 is because it's higher up on the normal curve, further away from the mean, which is 0 in this case. All right, go ahead and try that and check back with my answer. So you should have had Alice having an actual score of 41.448, which is what we anticipated, a higher score than what Steve had because she has a higher z-score. All right, last example. We've got example 5. It says Meg wonders if she should consider a career in the sciences because she does well in mathematics. However, she also does well in English. Determine the z-score for each of Meg's marks. Which subject is Meg better in relative to her peers? Okay, so looking at these marks, we can find out her z-score for English. Right? We'll take her English mark of 93, subtract that from the standard test results. So the mean is 77 and the standard deviation is 6.8. And if you do that, you get a value of 2.353. If we do this again for math, we can see, okay, 91 minus 74. So 91 is close to 93, what she got in English. The standard the means are close to 77 and 74, and the standard deviation is 5.4. Well, when we look at that, we get 3.148. So the nice thing is even though the actual scores and the actual data are quite different, when you get them to be z-scores, which is the reason why we use z-scores, is you can actually now compare the results. These are the same normal curves, right, that we're fitting them to, and we can see that her English mark fits lower on the normal curve than her math mark. So if I were to draw the normal curve here, run out of space, and we put this here at 0, 1, 2, 3. If we take her English mark as 2.35, so approximately here. And then if we look at her math mark, 3.14, that would be here. So quite a bit higher on the normal curve than is her English mark. So if you were to recommend to her which subject she's better in relative to her peers, we would say, well, you're much better in math relative to your peers. But that's relative, right? We got to remember that we're comparing results, and so it's always going to be relative to what we're looking at. So your z-score is going to be most powerful according to the data that you're collecting. So we can conclude math because your score is better. We're going to continue with this lesson in the next video, so thanks for joining me.